Hello, everyone. I'm Rupeng An. In the previous session, we talked about how we use LangChain to create multi-query retrieval, in which we expand a single query into multiple queries using large language model, and then we start uh, retrieve documents based on each version of the queries, and then we assemble those documents together to build a pipeline to answer the user's questions. So that is called multi-query retrieval. And in this section, we will continue talk about a highly related rack system called rack fusion. So the rack fusion strategy shares similarities with the multi-query retrieval strategy, except that now we apply a final re-ranking step to all the retrieved documents, because the multi-query retrieval can end up with many retrieved documents, and a re-ranking will be necessary to make sure that our generated message pertain to the most important documents rather than span across many different retrieved documents. So this re-ranking step makes use of the so-called reciprocal rank fusion, or RRF algorithm, which involves combining the ranks of different search results to produce a single unified ranking. By combining ranks from different queries, we pull the most relevant documents to the top of the final list. So to create a rack fusion, we can first create the prompt template. So we call it the prompt rack fusion. The template reads, "You are a helpful system that generates multiple search queries based on a single input query. Generate multiple search queries related to the question, and then the output." Okay. So this essentially is the same as what we implemented in the multi-query retrieval, because it does adopt the same strategy in the multi-query retrieval. The only difference is that now we can rank the retrieved documents. Okay, so the previous part are exactly the same. We can write a function to parse the rewritten queries in a list, and then we can build the query chain, which link the prompt rack fusion to the chat model, the large language model, and then parse the output. Okay. So if we run this, we will see that this is exactly what we implemented before in the multi-query retrieval, that we have now 4 different versions of the queries in a list. So the first item in the list is how to overcome writer's block when you don't know what to say. The second, benefits of walking in perfect weather for physical and mental health. 3 is important transparency, effective declaring the AI policy of students. And 4 is pro and cons of faculty disclosing the AI policy of students. Actually, because I intentionally wrote a terrible prompt, a terrible query. If you recall, the query we wrote is that I don't know what to say. The weather is perfect for a walk. Should faculty declare the air policy out or not to their students? So therefore, you will see that there are 4 queries generated from this chain, but only the last 2, number 3 and number 4, are relevant. Okay, and now we can write a function called reciprocal rank fusion. Basically, this is the algorithm we are going to use to re-rank the retrieved documents. So so this function takes a list of search results of each query. So a list of documents And then we apply this uh, the inner list of documents by sorting it based on relevance. Okay. Um, so I will not really go into detail of this function. I adopt this function again from the textbook, learning uh, LangChain, which is pre-released in O'Reilly Media. If you're interested in that book, definitely get a digital copy. But basically, this function is a way that we can re-rank documents based on relevance. Okay, and it has a hyperparameter called k, and a higher k indicates the lower ranked documents have more influence. Okay, so if the k is higher, we pay no more relevance. We pay more attention equally to the documents, but when k is lower, we pay more attention to the uh, uh, the most important, most relevant document. Okay. So let's implement this function and build a retrieval chain on that. So here we see that we have the query gen. We feed the list of queries to the retriever. Notice again, as in the multi uh, chain query, we implement the retriever.batch so that it can process multiple queries at the same time in a parallel fashion. And then we link that to the function we wrote, reciprocal rank fusion, in order to rank the documents. So that's about all you need to know for this rack fusion pipeline. Everything else remains the same. You provide a prompt. That prompt is answer the following question based on the context. And context will be just the retrieved and the re-ranked documents. The question will be original question, and then you can create a chain function to link them together. Okay, so if we apply this, it's going to run a little bit longer because one, we have multiple queries, so we retrieve multiple documents, and second, we also need to rank them. But it's not too bad. It comes up. So the answer is based on the context provided, the faculty should declare the AI policy to their students. It is recommended that faculty explain to students what it is and is not allowed around AI use in the classes. This includes acknowledging the use of AI tools, being responsible for the content and accuracy of any work submitted, and discuss do's and don'ts related to AI use, blah, 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 right? So this is a pretty comprehensive answer. Okay, now we have introduced the multi-query chain. We have introduced the rack fusion, and now let's move on to another interesting applications of rack pipeline called hypothetical document embeddings or hide. So the hide is a strategy that involves creating a hypothetical document based on the user's query. Because no, we may assume that if we just use a simple query and we calculate, for example, the cosine similarity between the query and the list of documents, then the matching may not be that good, right? And so therefore the height says that how about we create based on the query, we first create a hypothetical argument, a hypothetical document or article. For example, using the query as the title, we generate an entire article, and then we can embed that article and then compare the relevance of that article to the documents in the vector store. Right. In this case, we could identify a more relevant document, and it could be more trustworthy, right? Because the association between the two documents could be higher than the association between a simple one-sentence query and a document. Okay, so that is the idea. Implementation is very simple. Now we just create a prompt hide. it says, please write a scientific paper passage to answer the question, right? So given the question, it's going to write a scientific paper. Of course, it depends. You may not need a scientific paper. Sometimes you need maybe a news article. It will depends on the documents you are trying to retrieve. And then you can build a chain to generate this document from the prompt. So this is going to generate the article and then parse it um, a little bit, and then you can, if you invoke this chain, still use the query. The question should faculty be required to declare AI policy to their students, and then the output will be just an article, right, based on this topic provided. So say in the recent years, the integration of artificial intelligence technologies in educational setting has become increasingly prevalent. As such, the question of whether faculty should be required to declare AI policy for their students has garnered significant attention, blah, 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 right? So this is the entire article. And then you can build this retrieval chain by linking the generated doc chain with the retriever. Okay, so let's do that. And now we can start create this. This is still the old prompt we use. Answer the following question based on context. In this case, the context will still be retrieve the documents, and the question will be just the original question. We build them in a chain, so everything remains the same. So here we revoke the chain. We revoke the chain here. Then let's see whether this time we get the correct answer. So down the underlying, it first create using the retrieval chain. It first create the document. It first create the article based on the question, and then compare the generated article to the saved documents in the vector database to retrieve the relevant docs, and then it uses this prompt and the chat model to write the answer based on the retrieved docs and then provide the answer. Right. So the final result is based on the context provided, it is recommended the faculty declare the AI policy to students. This is important in order to help students understand the do's and don'ts of AI use, the limitation of generative AI, and to ensure academic integrity, blah, 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 right? So still pretty good comprehensive answer. And now let's talk about query routing. Okay, so although a single vector store is useful, but sometimes we may have multiple vector stores, right, containing maybe different type of data, right? So maybe or even besides vector stores, we may have a CSV file, or may have a SQL SQL file, right? So vector database is good for storing contextual data, maybe for example text data, whereas the CSV file is optimized for saving numerical data, whereas the SQL is SQL database is optimized for saving relational data, right? With many tables, and the tables are interrelated based on their primary key and the secondary key, etc. Right? So in this case, when the user posts a query, we need to route the query to the right data sources, right? Maybe to different vector stores, maybe to vector store, or a SQL or a CSV file, right? So in this case, we need to develop the query routing in order to assign the query to the right database. Right? So there are various ways that you can build query routing. Let's show you the first way, that is called logic routing. So in logic routing, we give the LLM knowledge of the various data sources at our disposal, and then that the LLM reason which data source to apply based on the user query. Right? So here, first we need to make sure that the LLM return the specific name of that database, right? To ensure that MLM always return the required database name, we can use the pandatic we illustrated this before. In the Panac, we can use the base model to create a class. We call it a route query class. So this class is going to route the user query to the most relevant data source. Okay. So here, so the data source is we used the attribute of literal here. So in this case, the literal function is going to make sure that it can only take specific values. In this case, we only have two values, that we have a Python docs file and we have a JS docs file. Okay, so we want the large language model to generate either the Python doc or the JSON doc. Okay, so therefore we restrict the data source to be one of these two values. Okay. And we also use the field function. So the field function is from Pydantic, which add metadata to the field. In this case, we use this ellipsis to indicate that the data source is a required field without default value. Okay, so it has to report either the Python doc or the JSON doc. Okay, so there's no default. And then I also optionally provide a description. Given a user question, choose which data source would be the most relevant for answering the question. Okay, so we define this Pythonic class. And now we can choose a large language model we want to use. And then remember, we use the vStructure output and provide the class as an argument, so that the chat model will always produce either the Python docs or JSON docs as the output. Okay. Here we provide a system message. You are an expert at routing a user question to the appropriate data source. Based on the programming language the question is referring to, route it to the relevant data source. And then I wrote this prompt. The prompt takes a system message, and the human message is just the question we impose. And then we can define this router chain. Okay, so let's do that. Okay, and now let's test this out. Okay, so here I provide a question. So this question is asking why the following code doesn't work. As you can see, this code is a Python code. So therefore, if the route function work correctly, it should return the Python doc. Okay. So one thing to make sure that is the name of this of the databases are important, because that is where the route function, the route chain is going to refer to, right? But if you call it something else, maybe say Apple docs, then the router won't work, because router can't really figure out what data are saved in this Apple docs named file. Okay, so make sure that the name is explicit. And then we have this, and then we invoke the question and see whether the returned result data source return the Python docs. Okay, so let's do that. Indeed, we have the Python docs returned, so it means that this router works. The router recognized that the query is about the Python code, so it referred to the Python doc. So another way that you can do that, so the previous way we route the task is through the LLM. The LLM decide whether this question query should be assigned to which doc. Okay, but the second way that you can do that is just an if-else statement. Okay. So sorry, I go too fast. Before we talk about the second routing, the first routing, in fact, is that we allow LLM to define to provide the results, basically referring to the specific name of the documents, and then we use the if-else statement to uh, return the specific document. Okay, and to the specific chains that you can manipulate with the document. Okay. So here you may say, no, create a function called truth route. And in the truth route, you have an if-else statement. So if the Python docs is included in the results data source, and then you may initiate this chain. This chain I did not specify, but could be a chain manipulating the Python document, maybe searching for a particular function, etc. And the second else is that if it's not Python doc, then it must be the JSON doc. Then they'll return the chain for JSON doc. Okay, so we call this hard routing because although you use large language model to produce to output a particular data source, but then you use if and else statement that are hard coded to do the routing. Okay, to return the chain for Python doc or return the chain for JSON doc. Okay, but besides the logic routing, there's a second routing, which we may call the soft routing, basically using large language model to do the routing instead of using the if-else statement. Okay? So the semantic routing, unlike logical routing, the semantic routing involves embedding various prompts that present various data sources alongside the user's query, and then performing vector similarity search to retrieve the most similar prompt. Okay? So, so basically, you could think of this as first we create some kind of metadata, or description about different data sources that you have, and then you just create a similarity search between the query and the description of the database. And then, based on the most similar, the highest cosine similarity score, you are going to do the routing. Okay, you are going to assign that particular database based on the description. Okay, so that is the idea. Here we create two prompts. So think about the first prompt is a description about anything regarding weather and climate. Okay? And the second description is about database, all about fire and emergent situations. Okay? So there's two prompts. The first prompt that we call the physics template. Probably we shouldn't use this name. This is confusing. We should maybe use climate template, and we call this maybe fire template. Okay. Let's do this change here. Climate template and fire template. Right. And then we can embed those two prompts. So this prompts describe the first database. This prompt define the second database. And we embed those two prompts and yeah, save the relevant embeddings. Right? And now we can define the function to route the question to prompt that represents the underlying database based on a simple similarity search between the query and between the embedded query and the embedded prompt for the database descriptions. Right? So this function called for query, and you need to embed their query. And after that, you can just calculate the cosine similarity between the query embedding and the prompt embedding. Okay. After that, you just get the prompt that is most similar to the query, based on the highest score of the embedding. So the similarity argmax is going to retrieve the index associated with its highest similarity score. and then you just return the prompt template. Um, from the most similar prompt. Okay. So let's test this out. We have a query. Queries would calling. Sorry for the misspelling. Would calling a fire department a good idea, and then we can invoke this prompt router, and that's printed out. Um, and then let's run this. As you can see, this the printed text is the prompt router. When we invoke it, the output is you are firefighter. You are at a great answering question about fire and emergency situations. Okay. Um, so that is exactly what we wrote here, right? Because the large language model through semantic similarity search, it identified this prompt, basically this description of the database matches the best with the query. Okay, so it returned that, and then you can build the entire semantic router this way. You can link that prompt router to a chat model, and then you can parse the output. Okay. Um, so if we invoke the semantic router, uh, you get yes, calling the fire department in emergency situation is always a good idea, blah blah blah, right? Uh, in reality, no, instead of just linking to the large language model, you probably link to another chain that going to do some searching on the particular database represented by the firefighter. Okay. Um, uh, so that is the semantic routing. And now let's talk about the query construction. Okay. Um, so the retrieval-augmented generation, or the RAG, is an effective strategy to embed and retrieve relevant unstructured data from vector store that we experiment with. But most data available for use in production applications can be structured and kept typically stored in relational databases like SQL, for example, MySQL, MySQL database, or Postgres database, or other relational databases. Okay. Um, and also, the unstructured data embedded in the vector store may also contain structured metadata. So therefore, no, the query construction refer to the process of transforming a natural language query into the query language of a database or data source you are interacting with. Okay. So, for example, translating your query, your question into a SQL language so that it can interact with the SQL database, right? Or no, serving as transforming the query into a Boolean operator that is going to do the filter search on the meta data of a vector database. Okay. Say for the second one, here is an example. Consider a query: what are movies about aliens? What are movies about aliens in the year 1980? So this question contains an unstructured topic, which is an alien, but also contains a structured component, basically a Boolean operator, year double equals to 1980, right? So in this case, now how we can use the metadata if we have a vector store, and in the vector store we have some metadata regarding the year of the movie. How can we search both semantically, on the text, as well as logically, using Boolean testing serving as filters of the metadata, okay, to augment this search. So that is called the text to metadata filter. Uh, and we are going to create a self-querying retriever, a specific retriever to retrieve the metadata as well as the semantic data from a vector database. Okay. So the self-querying retriever, basically the idea is a retriever that has the ability to query itself. Uh, so specifically, given any natural language query, the retriever uses a query construction LLM chain to write a structured query and then apply the structured query to its underlying vector store. So this will allow the retriever not only use the user input query for semantic similarity comparison with the contents of the stored document, but also extract the filters from the user query on the metadata of stored documents and to execute those filters. Right? So if you want to learn more about the self-querying retriever, you can take a look of the official LangChain document. But here we'll just briefly illustrate how this can be done, how to create a self-querying retriever. So first, let's create a vector store from a list of documents. Um, so notice that actually Face does not support self-querying retriever, so we have to use a different vector store. We'll use Chroma, which is another powerful vector index that is a local index we often use. Okay. So here you create a document, you create docs. This doc is just a list of documents, and notice that it has both, for each document, it contains both the page content, which is the content, the semantic content of the vector store, but also has some kind of metadata, right? So metadata year, rating, genre, and sometimes different metadata as director. Uh, so so documents have different metadata uh, and representing different year or director or rating or genre of a particular movie. Okay. And then we can, of course, create a vector store from the documents. We embed them, use OpenAI embeddings. So we create this vector store. And now, in order to initiate our querying retriever, we have to provide some information upfront about the metadata fields that our documents support, and then a short description of the document contents. So both are needed because the name of the metadata field, of course, will be used in metadata searching filtering. But the description is also going to be important because through which the large language model will be able to tell which particular metadata it should use to filter the results. Okay. So here you need to create using the attribute information. You create a list of metadata field information. So this is going to be used by the self-querying retriever. Okay. Okay. So here we provide the attribute information for the first metadata. The name is genre. The description, the genre of the movie, one of science fiction, comedy, drama, thriller, romance, action, animated. And the type is string. We provide the year with the description, year the movie was released, the name of the director, the name of movie director, and the rating. Description as a 1 to 10 rating of the movie. And also you need to provide a document content description. So this description is simply just a brief summary of movie. Okay. Okay, so now you have created this list of metadata field information. And you can initiate the large language model. Now you can build a self-query retriever chain. It called for the following arguments. You need to provide the large language model, the vector store, the document content description, which is just something about this database, and finally the metadata field info. Okay, so let's do that. Now the self-query chain is created. Now we can start asking some questions. Okay. So first, let's test only specify a filter. Okay, I want to watch a movie rated higher than 8.5. So ideally, this self-query retriever is going to retrieve the documents based on the metadata, in particular, the metadata pertaining to the field of rating. Okay, so let's see how this is done. Great. Now we retrieved the two movies with rating of 9.9 and rating of 8.6. Okay, so both are higher than 8.5. And now let's do it more complicated way, right? The example specify a query and a filter. Say has Greta Gerwig directed any movies about women. Okay, so in this case, they have to identify the director name. They also need to identify thematically any movie that in the page content, any movie about a woman. Okay, so let's see. And again, perfect, right? It identified the director using the meta search, but it also identified from page content. This one is the most relevant, a bunch of normal-sized women, right? Okay. And then we can try a composite filter with the question, what is the highly rated above 8.5 science fiction film, right? So this is going to look at both metadata, right? Metadata about the rating as well as the genre. Okay, so let's see here. Again, we are good. We have both ratings above 8.5, but we also have the science fiction film based on the genre. Okay. And actually, this is not this is the genre here, and I think it's also partially based on the page content as well. So it's not probably not only genre, but also taking into account the page content. Okay. But you get this idea, right? For example, this one, what is the movie after 1990, but before 2005 that all about boys and preferably is animated, right? So this is pretty complicated. You need to look for the genre, you need to look for the year. You also need to look at the thematically. Okay, so this is good. So it got a genre of animated year 1995. The page content is toys come alive and have a blast doing so. Okay, fantastic. And finally, let me show you how you can translate a question to an SQL or SQL query and then execute the query to get an answer. Okay. So basically, how to use LangChain to interact with a SQL using natural language. Okay, so first, I adopted the code from here, from the official LangChain documentation. If you're interested in the code, you can always take a look at the link, and I'll put the IP1B file in the show notes, so you'll be able to download that from GitHub. Okay. So here, I just define a function to generate an engine to interact with the Chinook database. So the Chinook database is a relational SQL database. Okay. When I build this engine, I use the SQL database. So this SQL database is a function provided by LangChain to interact with the SQL database. And after that, I'll just print out all the table names included in the SQL database. As you can see, there are many tables, including album, artist, customer, employee. Actually, I'm going to use this employee as an example, but other tables as well. It's actually pretty simple to build this NoSQL query. First, we define a large language model, And then we use this function, again, a function provided by LangChain called create SQL query chain. And it asks for two arguments. You need to provide the language model, you need to provide the SQL database. And then you can start invoke this chain. So the question is, how many employees are there? So if I ask this question, basically the create SQL query chain is going to convert or translate my natural language question to a SQL query, okay, so that it can be understood and processed by a SQL database. So let's see. Indeed, it creates a SQL language called select count employee ID as total employees from employee. So basically, if you understand SQL, basically it tells you that I'm going to look for the employee table, and from that, I'm going to count the employee ID. Okay, and I'm going to assign total employees as the variable name to store the count. So if there are, say, 100 employee IDs there, then the count will be equal to then the total employees is going to be equal to 100. Okay. Okay. But this step only translate your natural language query to SQL language, but without executing it on the database. To execute it, first you have to use the LangChain function called query SQL database tool. Okay, and you provide argument of the database. And then after that, you can uh, you can combine the query, the right query, which do the translation with the execute query. Okay, so in this case, the right query is going to, as previously documented, is going to translate your natural language query into a SQL language, and then it's going to use the SQL language to execute on the SQL database. So in this case, still, my question is how many employees are there? I invoke this overall chain, then it returns 8. So basically, it returns there are a total of 8 distinct employee IDs in that particular table called employee. Okay. So that's all for today, and we'll meet next time to talk about some other exciting LangChain functions, in particular how we can create a memory space for for the inquiry. So a user can keep asking questions to the same database to generate response. Thank you for watching.